Good morning, or good afternoon. Today we'll be talking about speed and acceleration sensors. So it will be, we can maybe call it an extension for last two lectures where we have been discussing position. We will discuss several principles about speed sensors, and this is only a selection of how well you can measure the speed of something. We'll be talking about linear speed and about angular speed. As you will see, both sensor types can be used for, well, the principles can be used for both. But some of them, like especially the first one, the electromagnetic, is used, for example, only for angular motion. So some are more suitable for angular motion, some are more suitable for linear motion. We will discuss about 5 principles. We will not discuss the purely mechanical principle as is used in old cars, for example, where it's really a mechanical speed sensor. But we will focus on the sensors that have some electrical output. So either an electrical signal, or it could be an optical sensor, or it could be a magnetic sensor, for example. But in all case, it will have some form of output that we can measure somehow. We will discuss the one example of the electromagnetic speed sensor, and that will be a sensor that we will use in the labs. And it will be a tachogenerator. And then the others, like the optoelectric, magnetic, and inductive, you have seen similar devices already last week, because this is very, very similar to the position sensor. So we will see again the similar principles. Let me start with the electromagnetic, which is called a DC tachogenerator. A DC tachogenerator is an electric machine that is very similar to a DC motor or DC generator. It is a device that uses the fact that when we have a coil in a magnetic field, we can pick up the voltage from this coil, and there will be an induced voltage if this coil is moving in this magnetic field. So it's basically an electrical generator. The construction has the following parts. It has a rotor, which is shown here. That's the winding part and the commutator, and of course the shaft. And then it has a stator, and the stator here is generating the magnetic flux. So the moving part is the winding here that is moving in the air gap, and the commutator. We are obtaining an induced voltage in the coil, and in order to transfer it from the rotor to the stator, we will need some brushes. So here there are at least 2 brushes that pick up the voltage from the commutator. The magnetic circuit in the stator is shown here, and it needs to be a closed magnetic circuit. So what you see here in the center, for example, is the stator part, and in this case it's a permanent magnet. So this permanent magnet produces a magnetic field, and this magnetic flux is going through the air gap, through the stator, and back into the permanent magnet. So it's a closed circuit. And here you have an example of a 2-pole stator, and the magnetic flux will go one part here and the other part on the right side. We will assume that this is a uniform magnetic circuit, so the magnetic flux will be the same in the left part and in the right part. So this is a stator part. So here this is fixed part, this is not moving, and the stator is not moving as well. What is moving is the coil that is in the air gap. So here this coil is rotating in the air gap. And this means that the coil will see a variable magnetic flux, and therefore there will be an induced voltage that we can measure. This variable voltage from the coil is then connected to the commutator, and the commutator acts as a mechanical rectifier. We are not using one section of the coil, but we are using several sections. So here is an example of a rotor. This is a DC motor, but the construction of a tachogenerator is very similar. And here you see we have more coils in the rotor. The winding is connected here in those slots, and this is the rotor magnetic circuit. So everything is from iron, because iron is a good material for magnetic circuits. It has a very high permeability, so it will conduct the magnetic flux in a good way, much better than air. And here you see that the coils are connected to the commutator. So there are more than one coil in the rotor, and we are able to pick this voltage from the coils. If we would use only one voltage from the one coil, we would see that it's an AC source. So it's an AC generator, and it would be a sinusoidal voltage. So if we would connect only one coil, we would see a sinusoidal voltage. We want to measure DC voltage, so this means that we will measure only the peaks of this sinusoidal voltage, and this means that we need to switch between the individual coils. So this is the task for the commutator. The coils are shifted, and the voltage will be shifted in time. So if you look on this picture, for example, the red curve will be the induced voltage in one coil, the yellow is in second coil, blue is in third coil, and so forth. So we are constantly switching between those coil sections, and this is done with the help of the commutator. So the commutator and brush, it acts together, and it is switching between the individual coils, so that when we look on the voltage output here, we will see just those peaks, and the DC voltage V0 will be proportional to speed. The higher the rate of change of magnetic flux, the higher the induced voltage. So the signal that we want to get from the DC tachogenerator is a DC voltage that is proportional to speed. Now if we describe this with an equation, we will see that the output voltage depends on the angular speed, that's what we want. It depends on the magnetic flux, but this is constant since this is produced by a permanent magnet. And then this constant CDC describes the construction. So it is a constant as well. So in other words, the voltage is directly proportional to angular speed. So this is a quite good sensor for angular speed. However, if we look more closely on its properties, it will be very important to use the correct load. This DC tachogenerator is a voltage source. So it means that if I take a current from it, there will be a voltage drop on its internal resistance. And the internal resistance in this case is relatively high, so I cannot take a really high current. It's not a generator that can be used to power a bulb, for example. So we need to watch very carefully about the load resistance. And the ideal load resistance for a voltage source is when the load resistance is going to infinity. In other words, I do not take any current. So if you look on specifications for tachogenerators, you will always find what is the recommended load resistance, so that you are taking the nominal current from it, and if the current is higher, the voltage will drop. The result will be that you will not be able to distinguish if you measure correctly. The most important information for the DC tachogenerator is the sensitivity. And the sensitivity means what is the slope of the output signal versus the input signal. The input signal in this case is speed, and the output signal in this case is voltage. So if we have a defined sensitivity, it is saying me how much is the voltage changing if there is a change in speed. For an unloaded output, the voltage will be linear, and it will have a high sensitivity. However, if you load the tachogenerator with some current, you will have a linear voltage drop on its internal resistance. This means that the output voltage will change. It will be smaller, but it will also be linear. So just by looking on the shape of the characteristic, you cannot tell at all if you measure correctly or not. Let's say we have a tachogenerator such as the one I have here, let's say 2 volts for 1000 RPM, and if I load it with some resistance, it can drop below those 2 volts, and I would think that the speed is smaller. So for this reason, if you look in some tables for tachogenerators, and always look what is the minimal recommended load resistance, and you have to keep it, because then you will have the correct characteristic and not some smaller voltage that you actually measure. This is the construction of the DC tachogenerator. So here you see that's the rotor, this is the stator. In some versions you have a shaft that you connect through a coupling to your application. In some versions, such as you see here, you don't have the shaft and you mount it directly in the machine that you are designing. I have here an example of such a DC tachogenerator. How does it look inside? So you see this is the coil that is moving. The coil is rotating in the air gap. It has more sections that are connected to the commutator, which is here on my right hand side, and here we have the brushes. In case of a DC tachogenerator, the brushes are made from silver wires. If this would be a DC motor, the typical material for brushes is carbon. The reason is that we want to have a small voltage drop, as small as possible, and this is achieved by the silver wires. So here in the center has the permanent magnet. The coil is rotating in the air gap, and then this stator iron conducts the magnetic flux back to the permanent magnet. The tachogenerator has relatively high voltage output. We will use it also in the labs. It has about 80 volts for 1000 RPM. If this is a smaller tachogenerator, the voltage will be smaller. So for example, this tachogenerator that I will use at the end of today's lecture has about 2 volts for 1000 RPM. So the voltage depends on size and on construction, and typically the larger the generator, the larger the voltage. You can also note that the output of the voltage has some ripple. So in other words, we want to look for the V0 voltage. That's the voltage corresponding to the speed. But we always have some voltage ripple. This is caused by the construction and by the fact that the commutator has a limited number of sections. If I would be able to build a larger machine with larger sections, larger number of coils, then I would be able to rectify the voltage in a better way, and then I would decrease the delta V. This delta V is quite significant because this will limit us the accuracy with which we can measure the speed. It has no information about the speed, so typically if the voltage is, let's say, 100 volts, the voltage ripple will be something like 1 or 2 volts roughly. So with a tachogenerator, you are typically not able to measure more accurately than within 1 or 2% of the range that you have available. So if you want some more accurate reading, you need some other principle than the tachogenerator. On the other hand, the DC tachogenerator is producing its own voltage, so we do not need any external power supply. It's just giving me the voltage that is proportional to speed, and I don't need any power supply. So it's a quite simple device, but it's not a good device for very accurate experiments. By very accurate, I mean here if I want to measure more accurately than, let's say, 1% of the range. In this table, you have a summary of some important information that we are looking for a DC tachogenerator. The most important here is the maximum speed range. It's a mechanical device. It's designed for some mechanical speed. It has to work with some centrifugal forces, for example. So here you see typically it's not going too much above 10,000 RPM. Here typical range is 4,000 RPM. Here we have 8,000 RPM. Here we have 12,000 RPM. So if you need some high-speed application, then tachogenerator is not a good idea. Here in the second line, you see what are the voltages. So for example, here 50 volts for 1000 RPM. This has also 50 volts for 1000 RPM, and so forth. This is like a quite typical value, something like 50 volts for larger generators. Small generators may have something like 1 or 2 volts for 1000 RPM. The maximum output current is related to the load that I can connect to the generator. So either you will find here the current, or you will find what is the minimum allowed resistance that you can connect to it, and if you go over it, then you will have a voltage drop. Of course, moment of inertia, if you have some very small device, you will significantly increase the moment of inertia of your device just by connecting the tachogenerator to the machine. What's going on? Something turns itself off. So it's a contact sensor. It needs a direct contact between the shaft with a coupling, so it's increasing the moment of inertia. We will see a little bit later that the other sensors are non-contact sensors, so they will not do this. Also, very important is linearity. So this is saying how far is it away from the ideal linear dependence of the voltage. Here you can see that it's not bad, 0.15, 0.5, so it's quite a linear output. The other data are not important right now. Maybe just the armature resistance here, 70, 50 ohms. So that's the resistance of the rotor winding. You see it's quite high compared to DC motors, for example. And therefore the current that we can take from this is low. Questions? Okay, good. So now let's move to the non-contact sensors. We can use an optoelectric sensor to measure position and to measure speed. We have seen a similar device last week as a position sensor. The principle is very simple. I install an object with some marks on my rotor. The marks here can be, for example, holes, or it can be a ring with teeth and gaps. And I detect if the light is being blocked or if it's not being blocked by the object that is moving. So for example, you can install a ring with holes or teeth on your machine. One example is here. You see this is a DC motor. Here it's the ring, and if I install an optical sensor that looks from one side on this ring and a detector from the other side, then I'm able to detect the motion. So from one side of the ring, you need to install a light source, which is a bulb, or if it can be an infrared LED. And from the other side, you install a light detector. This could be a photoresistor, photodiode, or a phototransistor. So if the light is passing through the hole or through the gap, you can see it, you have a signal. If it's blocked by the material, then you don't see the light and you don't have a signal. So on the output, here you typically see a rectangular signal, and you can count the frequency, and this will give you speed if you know how many holes you have in the ring. And if you start from some reference position, then by counting the number of pulses, you can also say position. But this would not work just with one pair of sensors. You would not be able to distinguish left or right with just one sensor. So in this case, it's just a speed sensor, but if you install two sensors with a defined shift and start from some defined position, then it could be also a relative position sensor. I have here some examples where it is used as a position sensor or as a speed sensor. So what you see here, it's a picture of an old computer mouse. The motion is transferred through this ball to this shaft and to this shaft, so it has two axes. And here you see the ring. That's a plastic ring with teeth and gaps. And here this pair is the pair of a light emitting diode, infrared, and a phototransistor. So this detects the motion. Here it counts pulses and it's saying you what was the position. The sensor can look also like this. So this is an integrated pair of LED and phototransistor or photodiode, and then the disk is moving in this slot, and you can count the pulses and you can get the speed. It can also work in this way. So this is a reflective sensor. So it's a package where you have the LED plus the phototransistor in one package, and you're looking for a reflection. So if this would be installed, for example, in this application, then I could look for reflection from this sticker, and I could get, again, rectangular signal, and I could measure speed of this disk, for example. So both approaches are used. It actually depends on the application, but I would say that this is a more common approach where you block the light with some material that is moving or rotating. Let me see if I have some examples here. Yeah, for example, this is an optical sensor with the slot. So one half is the light emitting diode, one half is the infrared phototransistor. It's embedded inside. We cannot see it through it because it's designed for infrared radiation, so it's not for visible light. The reflective sensor, well, no, this is still the version with the slot. So here in the slot there is a disk, and we can pick it up. Let me see. Yeah, this is just the code disk. You can see that here there's one teeth missing. Do you know why? Yes. We expect that if it's rotating with a constant speed, we will have a constant pulses from there. And if there is one missing, we can say this is my reference position. So then by the, let's say, signal processing, we can find the reference position. So we can use it also to find the zero position. Okay. So let me go to something else. We can use also inductive sensors to detect speed. We have seen inductive sensors also when we discussed the proximity sensors. So here it is similar. The difference is that this kind of inductive sensor does not need any power supply. So it can be a passive sensor. We don't need to power it, and we can just look on the voltage or on the voltage frequency as a function of speed. This is a sensor typically used in automotive applications because it's quite robust, and it can work in environments where when you have moisture, when you have dirt, and so on. What you see here is a permanent magnet, and this permanent magnet creates a magnetic field around it. It can be either an open magnetic circuit or a closed magnetic circuit. Here on this picture, it's shown as an open magnetic circuit where it will work as well. Around the permanent magnet, we have a pickup coil, and we will be looking for induced voltage in this pickup coil. There will be an induced voltage only if we have a change in magnetic flux. And the change of magnetic flux will be caused by placing different materials in front of the sensor. So this disc that you see here is from a ferromagnetic material. It is not working with anything else. So it needs to be iron. And if I place iron here in front of the sensor, you will have a different magnetic flux if the sensor looks on the teeth or if it is looking on the air gap. So when this disc is rotating, I will have a variation in magnetic flux, and therefore there will be an induced voltage in the pickup coil. Here is an example. It's a simulation of such a sensor. So what you see here is that this is the permanent magnet, this is the pickup coil, and this is the ferromagnetic disc that is rotating. And the color here is showing the magnetic flux density. So if the sensor is looking on the teeth, there is a different magnetic flux than there is if the sensor is looking on the air gap. So it's important to set the correct ratio between the teeth size and between the sensor size. If you use a too large sensor with a large diameter, it will make sort of average of the magnetic flux, and the signal will be very weak, and you will not be able to measure it. So this is one example when the diameter of the sensor is roughly 3 times larger than the teeth size. It works quite well. The typical signal that you see from the sensor looks like this. So it's a sinusoidal signal, and what you get of change of magnetic flux. So this is one. Let's say this is a sinusoidal dependence. This is phase shifted by 90 degrees, roughly. Anyway, it's a sinusoidal dependence. So the voltage that you will measure from this sensor is a sinusoidal voltage. By looking on the frequency of this voltage, you can measure the speed. So the speed is directly proportional to frequency. The inductive sensor typically is working in At what time do we start? We start at 12:30, not at 13:00. So what you see here is the ferromagnetic disk. The sensor needs to maintain a very small air gap. So this is typically, let's say, 1 millimeter. So it's very close. And here inside we have the magnet. This is a permanent magnet. Most often we don't need any strong magnetic field, so it can be a soft iron that has been magnetized. And around the sensor we have the pickup coil. So this is then placed, for example, in an engine block, and it's detecting the rotation of something that you have mounted in the motor. It can be a disc, for example. Here you see a typical application. So we have a wheel with teeth. This is acting as the source of the variation of magnetic flux, and this is the sensor itself. From the outside, it looks quite similar to an inductive proximity sensor. You can also use inductive proximity sensors in most applications, but you need to be very careful about the air gap size, air gap distance. Here you can see also that you can remove some teeth, and this allows you to get some reference position. So if you need to time some valves, for example, or some engine control, you can do it easily with this kind of sensor and with this free space where you don't have any teeth. Those sensors are used in automotive applications typically, either to time the engine control or, for example, to control the ABS system. Here you have an example of an automotive sensor based on this principle. It is sensitive to the air gap size, and it's also limited to non-zero speeds. The reason why is that if I have zero speed, or if the speed is too small, then the induced voltage will be very small and I will not be able to pick it up. So those sensors are limited, let's say, to frequencies higher than few hertz. 5-10 hertz is the minimal frequency where you can use this kind of sensor. So it's not a problem for engine timing, or if it's not a problem for ABS, because you assume that when you're standing still, you don't need ABS. Here you have some example data for this kind of sensor. So the maximal frequency is also limited. So we have a limitation for minimal frequency and maximal frequency. The maximal frequency is related to how fast can the signal, the sensor work, and it gives you the number of teeth that you need to use in your application. The higher the number of teeth and the higher the speed, then you can quite fast approach the maximum frequency again. You see the air gap size. So for this is 0.8 millimeters. That's roughly the standard value. So I would say about 1 millimeter is the normal distance. And you see how accurate this needs to be adjusted. So it is very important to have the correct air gap size. What happens with the signal if you change the air gap size is visible on this chart. It's the same sensor for different speeds and for different air gap sizes and different loads on the output. So for example, this curve is for 100 kilo ohms. That's the resistance of the input of my appliance or computer or whatever you use. So it's a high resistance, and I have high voltage output for 0.5 millimeters. If I decrease the load resistance, for example, by using a voltmeter with a different input resistance to 10 kilo ohms, this is what will happen. So here you see this is the same distance here and here, but I have a 10 times smaller resistance. And the result is that you have significantly decreased the range where this can work, because here, let's say the linear range was something, let's say here, 6,000 RPM. So up to 6,000 RPM I could use the sensor. Here, when I have used a smaller resistance, the linear section is somewhere around here. So I have, let's say, 1500. So just by using a different input with different input resistance, you have decreased significantly the range. A similar fact will be also happening with the change of air gap. So this curve is with 100 kilo ohms, 1 millimeter, so by 500 micrometers larger air gap, and this gives you a significantly smaller voltage. So here I had 6000 RPM, we had something like 180 volts. Here for this I have like 70 volts. So by increasing the air gap size, we have decreased the available voltage. And again, by using a different load for 10 kilo ohms, that's those dots. Here I am again back at 1500 and significantly smaller voltage. So this kind of sensor is quite sensitive to setting of the correct air gap size, and also you need to use the high input resistance of your voltmeter or of your controller. A similar behavior can be expected also from the magnetic sensor. It is also sensitive to the size of the air gap, but this sensor will be able to work also for zero speed. We will discuss two versions. One will use a source of magnetic field, which you see here on the left side, and the second will use the same disk like we have for the inductive sensor. What you see here on the left side is the version with an active source of magnetic field. So you can imagine this is like a tape, and you place the tape on your object. So this is a linear sensor, this is an angular sensor. It can be also vice versa. And here we have magnetized areas where we have south and north pole. And above it is a Hall sensor. And a Hall sensor is a sensor for magnetic field. So a Hall sensor is a piece of semiconductor material. And here we have two electrodes in this direction. And we pass current through these two electrodes. So there are two electrodes, and here the electrons are moving in this direction. So let's say from left to the right. Now if we place this piece of semiconductor inside a magnetic field that is oriented in a perpendicular direction, like this, then there will be a force that will act on the charge that is being transported in the material. So what will happen is that this force will change the trajectory of the electrons towards one side of this semiconductor material. And then if I have two electrodes here and here, then I will have here a negative pole, and here I will have a positive pole. So the Hall voltage that we measure here is a function of current, but it's also a function of the strength of the magnetic field. So this is how the Hall sensor works. And now I'm able to use it also as a speed sensor. So if I look here on the north pole, I will have one direction of the Hall voltage. If I'm looking on the south pole, I will have a reverse direction. So the output will be also a rectangular signal. And by measuring the frequency, I can measure the speed of my object. It works in a similar way also in this version when you have the passive disk. This disk needs to be ferromagnetic as well. So it's the same material like for the inductive sensor. We have a source of permanent magnet, but now we do not have a pickup coil, but we have a Hall sensor. So the Hall sensor is detecting the magnetic flux, and the magnetic flux will be different if the sensor looks on the teeth or if it is looking on the gap here. So the output is a rectangular signal. The magnetic sensors are also quite typical in the automotive industry for the same purposes like the inductive sensors. So what you see here, this and this, are the automotive sensors, and those are industrial sensors like proximity sensors and switches, for example. So in both of them, it's this principle, a permanent magnet with the Hall sensor that is here on top of the device. I don't have any Hall sensor with me, but we have one in the lab. You have probably seen it for position 2 when there's one rotating disc, so you will have the chance to see it again. The Hall sensors are again quite sensitive to setting the correct distance. So in the manual you'll find what's the distance that you should keep. So for example, in this table, it's again an automotive sensor. They say 0.5 to 1.4 millimeters. So it's roughly the same distance as an inductive sensor. You can see we are also limited on the maximum frequency. So it's again roughly the same value like for inductive sensors. So a few kilohertz, 10 kilohertz, 15 kilohertz. What you see here again are two examples of automotive sensors. They say from 0 hertz to 15 kilohertz in one version. In another version there is a high pass filter, so from 2 hertz to 15 kilohertz, no, 15 hertz in this case. I think there is a K missing. And in this you see they limit it above 1 hertz up to 15 kilohertz. So not all sensors based on this are able to work from 0 speed, but still 1 hertz frequency, that's quite low. You can see the power supply voltage range here from 4.5 volt to 18, so that's well within the normal voltage that we have in industrial applications, which is 12 volts, sometimes it's 36 volts. In automotive applications, this normal voltage is like 12 volts. Okay, questions? Okay, fine. So the last sensor for speed will not be exactly a sensor, but it will be a principle that you can use to measure speed when you need it, and you are looking for speed of something, but you don't want to have any signal output. So it's like a handheld instrument that looks like this, and you use it to get speed. This instrument is a stroboscope. It has one important component. It is I'm unsure why it's in Czech, but this should be a bulb, and we can change the frequency with which the bulb is flashing. And the assumption is that if the light is on, I will see a reflection from some reflecting object that is placed on the rotating part. So for example, here in my application, the rotating part is this one, and the reflective sticker is this white sticker. And we'll be looking for the reflection from this white sticker. When the light is off, we will not see any reflection because the movement is so fast that our eyes cannot see it. What you see here is the situation when the frequency of flashes is larger than the frequency of rotation. So for example, here, when this will be on, I will see the reflection. So now I have seen the reflection in this position. Now I have seen the reflection in this position. Now I will see it here. In other words, the position of this sticker seems to be moving. So this means that the frequency of the flashes and the frequency of rotation is not equal. When the reflection is moving against the actual direction of rotation, it means that the frequency of the flashes is larger than the frequency of the rotation. If I have a different situation, I have a smaller frequency of flashes, then the reflective mark will move one entire revolution and something more. So in this case, we will see the reflection is, now I have seen it in this position. Now I will see it in this position because the disk is moving faster than the light is flashing. So it will make one complete revolution plus something. So in this case, it appears as the sticker is moving in the same direction as the disk is rotating. The situation that I want to achieve is that I have exactly the same frequency with the disk as I have here with the flashes. So what I see here is that I will see always the reflection at a constant position, and it appears as the disk is standing still. So the sticker is not moving, although I can hear or feel that something is happening, and I will see here a constant position. In this case, I know that the frequency of the flashes is the same like the frequency of rotation, and I can read on the display of the stroboscope what is the frequency. Let me try it. So let's see if we can try it. I cannot try it because it does not fit into the plug. So let's see if do you see some electrical plug near? Okay, so here we have the fluorescent bulb, and when I push the trigger, we'll see that this is flashing. Someone has some problems with flashing lights? No? Okay, so this is what is happening. So here now we have flashes, and we can adjust the frequency of the flashing. Here on the back side, we have a display with frequency, so I can see what frequency do I have. And now we'll try to make this work. And I will turn it on. Here we'll see that this is rotating, and we will have the chance to set the speed of it. So now I can change the speed of my motor, and now if I turn this on, we will see, probably turn off the lights. and we should be able to see the reflections. So here we have the sticker, and if I turn the stroboscope on, we will see that the sticker appears to be moving slowly. And now if I adjust the frequency, well, let's move it closer a little bit. So like this, it's probably a little bit better. So here we see the reflection. And now if I change the frequency of flashing, I am changing the speed. And now the sticker, let's see, let's try this. No, let's change the range. Well, let me increase the speed a little bit. So now the sticker is almost standing still. You see here, it appears that it's standing still, but I know that it's moving. So right now, it's standing still, and here I can read it's 1590 RPM. But it's important to measure correctly with the stroboscope. For example, if I change the frequency of flashes, right now you can't probably see it, but there are two stickers visible. And the reason is that now I have half the frequency of the flashes compared to the frequency of rotation. So this is fine. I can see that there are no two stickers, but I see two stickers. So it means that I have too low frequency. On the other hand, if I use too high frequency, something like 3000 something, no, now I have I have double the frequency. So now I see two stickers. I see 3300. But if my frequency is too low, the sticker will pass twice before I see it, and I will not be able to distinguish this. So with a stroboscope, it's important that you start always from the highest frequency. You see two or three stickers, and then you know that you should decrease the frequency. So this is an optical instrument, but it does not give you any signal on the output, but it's quite useful and to have it as a handheld instrument. So we will be also working with the stroboscope in the lab classes. So remember that if you see two reflections, such as in this position and in this position, then the frequency is doubled compared to the frequency of the flashes. For example, if you see this, one reflection here, one here, one here, you have three times the frequency. So with a stroboscope, you should always start with the highest frequency of flashes, and you will see two reflections, and then it's correct. If you start from the lowest setting, then something like this will happen. The sticker will pass two times, and you will not be able to see that. So we will have also a chance to try this out in the labs. Okay, and we'll finish with accelerometers. Accelerometers are quite useful because they do not measure only acceleration, but they measure also the direction of gravitational force. So, for example, well, all of you have accelerometers in cell phones when this orients the screen, if it should be horizontal or vertical, for example, if it's a smartphone. Accelerometers, they, well, in most cases, they do not measure acceleration directly, but we use the effect, the force that is creating by acceleration, and that's the force. So we'll be looking for the inertial force that is created as the effect of acceleration or gravitation. There are many principles that you have here in the table used for accelerometers. We will discuss only one of them, and we will discuss only the capacitive displacement accelerometer. It's the most common in applications like cell phones, airbag control, hard drive control, and so forth. So this is just a table that summarizes in what frequencies you can use the accelerometers. The accelerometer can be used also as a vibration sensor. And for example, here you see capacitive bridge. That's the one that we will discuss, or capacitive bridge of piezoresistive elements. Anyway, it's good for lower frequencies. So if you want to use it in a cell phone or in ABS, then it's fine. If you want to use it as a vibration sensor for high frequencies, then you have to use a piezoelectric sensor, which on the other hand is not working for low frequencies. So again, by application, you need to select the correct sensor principle. So we will discuss only this capacitive bridge sensor. The principle is quite easy. We are looking for the effect of the inertial force on a beam, and we measure the distance between the mass and some fixed frame. So the principle is shown here. We have a mass, seismic mass, attached on some beam. And here, this is a base plate, it's a fixed frame. Now, if I have an object like this, let's say this is my mass, and if I apply acceleration, and this is the beam, and the acceleration will go upwards, so this will happen, and then when the acceleration is constant, it will go back in the original position. So I'm basically looking for the distance between the mass and between the electrode, and this can be measured very accurately with a capacitive position sensor. So we're back at the position sensor in a capacitive version. So typically it's done in this way. Here we have two fixed electrodes, so it's a differential capacitive sensor. So those two electrodes are attached to the so if the central electrode is moving to the left, then this distance is decreasing, capacity is increasing, and this distance is increasing and capacity is decreasing. It's connected to a bridge circuit, which typically looks like this. This is this representation. So one capacitor is decreasing, one capacitor is increasing, and this will unbalance the bridge and will be able to get the distance. Today's accelerometers are based on silicon, and they are micro-manufactured with the same technology or similar technology like integrated circuits. What you see here are some examples. So here in this picture you see this is a seismic mass that is moving. The electrodes attached are this one, and so forth. So there are multiple electrodes connected together, and this are the electrodes that are connected to the frame. So this is a 2-axis accelerometer. When the mass is moving in this direction, then I measure it with this set of electrodes. When it's moving in this direction, then I measure it with this set of electrodes. The detail of the electrodes can be seen here. So again, this is fixed and this is moving. So when this seismic mass moves in this direction, then here this capacity is increasing and this capacity is decreasing. You can see that those capacitors are connected in parallel, so we are trying to increase the capacity so that we are able to measure it. We'll see a video how those sensors are manufactured and also for what applications. Here we have an example of such a capacitive accelerometer. You can get them in 1-axis, 2-axis, 3-axis versions, depending on the application that you need. Here I have a few examples. So those are the accelerometers. I think that all of them are 3-axial accelerometers. Let's take a look on the video. Takes about, I think, 4 minutes. So I have to find it first. Oh, it's slow. There seems to be some problem with internet access. I can't get to the video. So I will try to find the video later at the end of the lecture. Let's summarize the properties of those accelerometers. The capacitive accelerometers were originally developed for automotive applications. So if you crash into something, the deceleration is large, and then the airbag is fired. So you will find different acceleration ranges. Here you have an example of an accelerometer between 1.5 and 6 Gs. You can find accelerometers for different accelerations, like something like 10 or 20 Gs. In all cases, you need an output. The output is, in some cases, an analog signal, a voltage. Here you see an example, for example, 1 volt for 1 G output. So if you use it to measure the direction of rotation of your device, then it will have always 1 G unless you move it, and you will read from 3-axis. In some cases, you need a digital bus, so I2C or SPI buses are the typical bus that you will find here. I2C is a 2-wire bus. 1 wire is data, 1 wire is clock. SPI is a 3-wire bus, which is faster, but you don't need it for accelerometers usually. So you read either the number or you read the analog voltage that corresponds to the output of the acceleration. The accelerometers can be obtained in different versions. The difference is in how many axes you have available. So in some applications you need two, mostly you need three to orient yourself in space. So even the 3-axis accelerometers are quite cheap today. The cost is not that significant compared to the remaining electronic circuits. Okay, and the last device I would like to talk about is a gyroscope. A gyroscope sensor is very similar to the accelerometer. The difference is that accelerometer measures the linear acceleration. A gyroscope measures the angular acceleration. So typically you need to combine both if you want to have some usable signal. If you want to build a control system for a quadrotor plane or whatever is flying, you typically need to fuse the signal from a gyroscope with an accelerometer to make it work. The gyroscope I will show you are taking the advantage of the Coriolis force. So we, in fact, measure the effect of the Coriolis force on an object. And the detection is done again with a capacitive position sensor. So we will see that the structure of a MEMS gyroscope is very similar to the structure of a MEMS accelerometer. MEMS stands for micro electromechanical system. So for gyroscope, we have a mass. That's the same like for an accelerometer. But now we have the mass that is moving. So here you see it's either moving automatically or we imply this motion. And what we want to measure is this angular velocity or its angular acceleration. And when we have a mass that is moving and rotating at the same time, there will be a Coriolis force that is acting on this mass. And the Coriolis force is proportional to the angular velocity and proportional to the speed. So when we force this speed, this motion to be constant, then the force that we measure is directly proportional to the angular speed. We can measure the effect of the force in the same way like we did for an accelerometer. So if this mass is attached on a beam, then we can measure how is the distance of this mass changing related to a fixed frame. So a gyroscope, based on this principle, is working like this. We have a set of electrodes attached to a mass, and we use two masses here, and between them we have a spring. So let's say this is one mass, this is a second mass, and we imply this motion. So we imply this linear motion between the mass. We can measure the distance between the mass and the central frame. So now we have this motion, and now I'm rotating the masses, and this applies, let's say, call it additional twisting that we have. And this twisting will do this. We'll have different distance between one mass and the fixed frame and the other mass and the fixed frame. So this is again sensed in a capacitive sensor, capacitive position sensor. So what you see here, that's an example of such a gyroscope. You see this is a mass here, and we have one set of electrodes here and another set of electrodes over there. So in total view here we have the set of electrodes here and here, and when this is moving along this axis, if it's moving like this, we have a different distance between this capacitive sensor and between this capacitive sensor. So this allows us to detect the rotation in this axis. If you need a more axial gyroscope, you repeat that in different directions. So at the end, you will typically find 1, 2, or 3 axial gyroscopes. So it's similar to the accelerometer. The added block is that we need to imply this motion between the electrodes. And this is done with electrostatic field. So what you will find here is the driving circuit. This is an example of a 2-axial gyroscope. So you have a driving circuit, and here we have the amplifier that is picking up the distance between the electrodes. So it's picking up the distance between these electrodes here and these electrodes over there. We need to remove the influence of this motion, because we imply that. So here you measure the motion of the driving circuit, and you basically subtract it or demodulate it from the signal. And what you have on the output is a signal that is proportional to the angular acceleration. This is one channel in axis Z, and this is one channel in the x-axis. The data sheet of the gyroscope, the most important information is the output signal as a function of the input. So again, sensitivity. So typically something like this. So this is a sensor with a voltage output, and here, so you see millivolts per dps, it's degrees per second. So how many millivolts you will have if the speed is big. You can see also the measurement range. So 1500 degrees per second. That's roughly 5 revolutions per minute, per second. So this gives you roughly an idea in what applications this could be used. And at the end, we typically combine a gyroscope, an accelerometer, eventually a pressure sensor, and a magnetometer in something that's called an inertial measurement unit. So it's used for airplane navigation. What you see here on the left side is, let's say, the Profi version, but it has those 4 sensors. This is, let's say, the hobby version, which you can use for hobby airplanes or quadrotor planes, for example. They both have the same sensors. The difference is in speed, in reliability, in robustness, and so on. So typically, you have a 3-axial gyroscope, 3-axial accelerometer, 3-axial magnetometer. That's like an electronic compass. And here you have a pressure sensor to get the altitude above sea level, and you have temperature sensor. So this gives you some data. And the output here, in this case, this is an SPA bus, a 4-wire digital bus, but you can have any other kind of communication. I believe that this sensor has serial line, like normal serial line. This is an example of the ranges that you can expect. So plus minus 18 Gs, magnetometer. That's a magnetometer to get the heading. So it does not need to measure strong magnetic fields. The angular velocity, it's not given, but I would expect a similar range like you see here. So something like 400 degrees per second. So this is roughly 1 revolution per second. So about 3,600 RPM. And the digital pressure sensor, will be talking about pressure sensors, I think, next week. And this is used to measure the altitude above sea level.